Welcome students. Myself Amrita Saha from Department of Information Technology of Haldia Institute of Technology, and for today's lecture my topic of discussion would be on Introduction to Finite Automata. Well, before I could start with my lecture, let me just give you a brief introduction of finite automata. Well, this finite automata is comprised of two terms. One is finite and the other one is automata. If you locate or if you try to see the word automata, it has got some sort of pronounceable symmetry with the word automatic. Like in computers, we usually see that the processes appear to occur automatically. That means the input is provided to that system and we get the output, and some sort of internal operations do take place. So what happens is, suppose this is a machine and to this we are providing some sort of input. What we usually see is that on giving an input we get an corresponding output, but intermediately within the system some sort of operations that do take place by the CPU. But in reality what happens, this input that is being fed to this machine is converted into a machine understandable format, and we know that a machine understandable format is in the form of zeros and ones. After that this is being fed to the CPU where the internal operations do take place. After that the result is generated, which is also in this format 0 and 1, and then it is converted into a human understandable format. So this subject or this topic focuses on how to design such machines. If you see the definition, see it is already written that it is a mathematical model which contains finite number of states and transitions defined between them, and it provides the simplest model of a computing device. That means here we will be focusing on how to design such machines. So there are few characteristics that are associated with this finite automata. If I focus on those characteristics, it would be, first one is my input. As you can see, these are the inputs that are being provided or that are being fed to this machine, and at the same time the second characteristic is my output. The third one is state. The fourth element is my transition. And the fifth one is output. Alphabet. Now, what kind of output is being generated, that depends on the type of machine, which I'll shortly explain in some time. But before that, if I focus on these three elements, that means my machine is going to accept some sort of input which is given to this machine in some clock cycles. That means in every clock cycle the input is being fed to the machine and we are getting some sort of output. Now what operations are occurring within this machine, that is discussed later, but as of now this machine is going to accept some input and it will generate some sort of output. There are some associated states with this machine, and as the name suggests, finite automata, so finite automata suggests that finite number of states will be used to design such machines. Let us just focus on a few examples, and before that, first we should know in which cases or in which areas this is applicable. As you can see, it is written that the main usefulness of automata theory is in the compiler design. The first phase of the compiler is the lexical analyzer, in which there is in a varied amounts this is used. The second one is the working principle of a software that is used for checking the behavior of a digital circuits. The third one is it is also applied in the natural language processing, and finally it is also used for designing a software in which we need to count the occurrence of a particular word in a large text or in a pattern. So this finite automata can be classified into two broad categories. One category is the finite automata with output, and the second category is finite automata without output, which can further be classified into two categories further: the mealy machine, Murray machine, and within the finite automata without output, DFA, NFA and epsilon NFA. It is to be noted that all these machines are coming under the category of language recognizer. That means to this machine, if we feed some sort of string, it is either going to accept that string or it is going to reject that string. So these are the two probable output in case of finite automata without output. That means we are feeding some sort of input, and what will be the output? The two probable output would be acceptance or it is rejected. But in the classification, in the finite automata with output, that is, either we design the machine using this mealy machine or a Murray machine. To this, if we feed an input, the resultant is going to be a output, a particular output. Say for example, under this category, one common example that you can take is 1's complement. That means if you feed a binary sequence that is formed of sequence of zeros and ones to this machine, what will be the output? The output will be a 1's complement of that binary sequence. That means we are giving some sort of input, and what we are getting as output is an output that is based on some zeros and ones, which was not happening in case of a finite automata without output. Now, let us just discuss the first type of finite automata, that is the deterministic finite automata. The word says it is deterministic. That means for a particular input symbol, a particular state will move to one unique state only. Let us just see. A deterministic finite automata can be expressed in a 5-tuple form. That means using these 5 elements, we can define a deterministic finite automata. Let us just see what are these 5 elements. The Q indicates the finite number of states. That means we are going to use some finite, that means the number of states is countable, and using those states we will be able to design our machine. Next is the input alphabet. Now, the input alphabet contains the symbols that your string is going to contain. Next is the transition function. The transition function says that a particular state, on getting an input alphabet, it is going to move to one unique state only. This is what the transition function says, and it is the most important factor which differentiates the DFA, the NFA and the epsilon NFA. The Q0, this Q0 indicates that this is the start state. The start state can also be indicated with an arrow. So whichever state, to whichever state there is an arrow associated with it, it indicates what? It is indicating my start state. And F is a set of final state, which is denoted by 2 double concentric circles. It is not mandatory that a particular DFA can contain one single final state only. It can contain one final state or it can contain multiple final state. But the mandatory thing is that a particular finite DFA or NFA or epsilon NFA must contain one single initial state only. So using these 5 elements, we can easily define a deterministic finite automata. As you can see, an example of deterministic finite automata is also used. Here we have made use of 3 states, and these states have been named as Q0, Q1, Q2. That is why it has been written within the set Q. Along with it, the second element was the input symbol. This input symbol, for this case, we have used A and B. Input symbols are the input alphabet contains the basic symbols that are to be used within the string. Next is the start state. For this example, the arrow is being associated with the Q0, that is, for this example, Q0 becomes my start state and the final state is depicted by Q2. And the transition function, as I have said, in case of a deterministic, that means the word deterministic means a particular state on getting an input symbol will move to one unique state only. It is not that a particular input symbol on getting a particular input symbol, a particular state is moving to multiple states. Then it is not satisfying the criteria of deterministic. So the transition function says that this is the state and on getting an input symbol, it is moving to one unique state only. As explained, as you can see that each of these individual states on getting an input symbol is moving to one of the states, and that is why it is called as deterministic. For every input on a state, there is exactly one transition. It is to be remembered that whenever for a problem statement we are drawing a DFA, one has to make sure that for every state and for every input symbol, all the transitions has to be specified. It is not that, for this case, we know that sigma is comprised of two symbols, that is A comma B. So it might happen that while we are drawing a DFA, we have specified that for input symbol A to which state Q0 should move on to, but we have forgotten to specify to which state Q0 should move on getting a B. In that case, it won't be a complete DFA. A complete DFA is where for every state you have defined for which input symbol to which state it should head on to. That is a complete DFA. So let us just take an example. We know, as of now, we know that a DFA is comprised of 5 individual elements. One is the states, finite number of states, that is depicted with Q. Then is the sigma. Then is the transition function. Then is my Q0, which indicates the initial state, and finally F indicates the final state. So for a very problem statement, the very first thing that I need to do is that first you read the question and you write what is the sigma for that particular question, and then you write the language. Language indicates that what kind of strings is being contained in that set, and that nature of the strings will be depicted in the question itself. Like for this example, it is written, construct a DFA that accept set of all strings over A comma B of length 2. So as soon as I read this question, first thing that came to my mind is that the sigma has been specified and the condition is also being given to me. What is the condition? The condition is that it should accept set of all strings with length 2. So in that case, we won't be writing the strings in the language haphazardly. We will be starting it in a very methodical way. That means first we will look for whether is there any zero length string that is being contained in this language. If yes, we will include it in that set. If not, we will be moving on to one length string. Is there any one length string? So one length string possible, that is A and B. But A and B is not satisfying this criteria, that is, it is not of length 2. So we will be excluding this and we will be moving on to the 2 length string. So if we have a 2 length string, something like this, so we have 2 vacant spaces, and for every vacant space we have 2 choices. That means for this space we have 2 choices, that is A or B. And for each of these individual choices, we can set either A or either B in this place, and for B there again is 2 choices, that is A or B. That means the number of strings possible is AA, AB, BA and BB. So this satisfied my condition. Achha. Next we will be moving on that whether any 3 length string is possible or not. If you look carefully, the 3 length string is not at all satisfying this condition, so we will be excluding that, and subsequently 4 length, 5th length will not be checked because it will never satisfy the given condition. So what we can see that this language is a finite language. It is not infinite language. That means all the elements are countable. Now the next thing that one has to do is that first you make a rough prototype of a given DFA. That means if you take a natural example, if I want to build a building, if I want to make a building, will I bring the cement or bricks in the very first step? No, I'm not going to do that. What I will do is that I will be drawing a prototype first, and then subsequently I will be making the changes. Much in the same way, I'll do it for a DFA. The working principle says that you choose the smallest length string, and based on that you draw a rough structure for that DFA. That means if I take AB as my smallest length string, then for this string the DFA would be something like this. It would be something like this. That means when I am feeding to this machine a string that is A and AB, then what will happen? It will somewhat look like this. It will somehow look like this, that initially I am at Q0. I am presently at Q0, and as soon as I get a, I will be moving on to an intermediate state, that is Q1. And if a B comes, I will be moving on to Q2. That is, now my string, I can say it is accepted. If at all it happens that on scanning the string from left to right, you are stuck in some intermediate state. Intermediate state in this case would be either Q0 or Q1. In that case, it won't be accepted. It would be accepted only when on scanning the string I reach to the final state, that is Q2. So as we can see, that is this a complete DFA? No, not at all, because for Q0 state I have defined where to go for A, but I haven't defined where to go if a B comes. Similarly, for a Q state Q1, I have defined where to go for an input B, but I haven't defined where to go for an input A. So this DFA cannot be called as a complete DFA. So now I will be taking the transitions, or now I will be taking the input symbols sequentially, and then we will be analyzing. Now if I place a B, what could be the possible strings that is accepted? As you can see, AB will be accepted, then BB will be accepted. These two strings will be accepted. Now what to do if I want this machine to accept AA and BA? In that case, if I associate this symbol A to this transition, then we can easily see that all the four strings are accepted. That means AA is also accepted, AB is also accepted, BA is also accepted, and BB is also accepted. But is this a complete DFA? Not at all. Why? Because for Q0 I have defined for A and B, for Q1 I have defined for A and B, but for Q2 I haven't defined where to go if a A comes or if a B comes. In that case, I have to add an extra state, and I have to specify that if any other symbol comes, it will move again to an intermediate state, that is Q3, because to this state you can never assure, rather to this machine you can never assure that you will be feeding only the 2 length strings. To this machine I can give a 2 length string also, a 3 length string also, or a n length string also. But what the machine should do is, it should accept only those strings whose length is 2, and otherwise it should reject all the other strings that are of length greater than 2. Now if you feed any string to this machine, what you can see is that either it will accept it or it will reject it. In which cases it will accept? If the length of the string is equal to 2, and in which cases it will be rejected? If the length of the string is exceeding 2, or if the length of the string is less than 2. What if I feed to this machine a string that is epsilon? Then it will be stuck in this Q0 state only, and it won't be moving further. And we know that a string will be accepted only when this, on scanning the string, if I reach to the final state, then only my string is going to be accepted, otherwise it will be stuck in some intermediate state. For this example, Q0, Q1, Q3 are my intermediate states, and Q2 becomes my final state. Let us just take one more example and then we will be moving on. The next problem says that construct a DFA that accepts all strings over A, B that contains ABA as substring. So the very first thing, as I said, for a given problem statement, first you write what is the sigma. So the sigma is A, B, only two symbols are used for this problem statement, and then you write the language. For language, first you start from the least length string that is being accepted. If you look properly, 0 length string will be accepted? No, because it is not satisfying the criteria. 1 length, 2 length? No. 3 length? Yes. 3 length string, that too it is containing ABA. If it contains ABA, then only it is going to accept, otherwise not. So 3 length string, only one combination is acceptable, that is ABA and nothing other than that. After that, you can go for checking whether the other 4 length strings, then you can find out there are multiple 4 length strings possible, and subsequently 5 length, 6 length, so on. You don't need to write all the strings, you just write the preliminary strings, and then from that you can get an idea of what is the nature of that machine, and from there you can draw the state representation. Well, this is an infinite language. So as I have said before, for a given string, you first draw a rough prototype of the DFA. That means a rough prototype should contain, see, ABA. That means this is the rough prototype where ABA is the smallest length string that is accepted by the given DFA. For now, I will not be numbering those states. Let the states remain as it is. Later on, we will be numbering it. So, as we can see that, okay, ABA is being accepted by the DFA. But is it a complete DFA? No, because for all the states, I have not marked the transitions where to go for A or a B. That means for every state, we have to mark for which input symbols to which state it should head on to. As you can see that the first state, I have marked where to go for a A, but I haven't marked where to go or which state to go to if a B comes. So let us just take, or let us just initialize the DFA further. Let's just take the examples. What if a B comes? Multiple B comes. Should I reject that string, or should that machine reject that particular string that contains only B's? No. Why? Because there is a possibility that in the future ABA might come. So I'll just wait in the first state and wait for whom? Wait for a ABA. So I can add a self loop to this state and mark it with B. Something like this. That means I am waiting in the initial state for whom? For an ABA. Now, is this state complete? Yes, because for this state I have marked for A and for B both. Now, if I want to reach the second state, then that means I have already seen one single A in the string. Now, if I want to move ahead, or rather if a multiple A comes, that means 3 or 4 or 5 A's, should I reject that string? No, I should wait in the second state and wait for whom? Wait for a BA to come. If one A comes or two multiple A's comes, it doesn't affect the condition anyway. So I will be waiting in the second state and wait for whom? Wait for a BA. Is this state complete? Of course, yes, this state is complete. Next, for the third state, A has been defined, but we don't know what to do if a B comes. Now, to reach this third state, what we have seen in the input string, we have seen that AB has already come. Now what if a B comes? Should I add B to this transition? No. If I add B to this transition, what will happen? It will accept ABB also. So what we will do, if a B comes, again I will make that point to the first state. Why? Because if a B comes, then again it has to wait for a AB. Then only it will be accepting the string, otherwise not. So if a B comes, I will be directly moving to the first state and wait for a ABA. Next, the third state is complete, and then comes the final state. See, whenever we are talking of ABA as substring, that means it doesn't care about where is that ABA present in that string. It might happen that the string is starting with an ABA, or it might happen that the string is ending with an ABA, or it might happen that the ABA is occurring somewhere in the middle of the string. So the question says that as soon as you encounter this ABA, you simply accept it. Whatever it is containing other symbols, we won't be caring about that. So once we have reached to the fourth state, or rather I should say, once we have reached the final state, I don't care what comes after it. I will simply accept any combination of A's or B's that comes after an ABA. That means a condition of this. Whenever we are talking of substring, always remember, once we have encountered an ABA, it doesn't matter where you are or what symbols are present after that ABA, it will anyway accept that string. So that is why I have added a self loop. Whenever you are adding a self loop in a DFA, you make sure that in which cases it should be applicable. It is applicable in those cases only where it doesn't matter to us the number of occurrences of that particular input symbol. Suppose if I have to remember the number of occurrences of an input symbol, then I can never add a self loop to that state, because as soon as we are adding a self loop, it means now we cannot make any count of how many number of A's or how many number of B's have arrived. So we will be adding a direct transition from one state to the other state only in case we have to remember the occurrences of a particular input symbol in the string. So basically this is how we design a DFA. So if I revise the overall thing once again, the working principle says that first, for a given problem statement, you just write the sigma, what is the input symbol, and then you write the language. The language, while you are writing the language, don't write it in a haphazard manner. You just start it from the initial phase. That means check whether a zero-length string is acceptable or not. If yes, include it in that set. Then one-length string, then two-length string. Once you have written up till 2 or 3-length string, no need to write further. You just put a dot dot and then you just close the bracket. After that, you take the smallest possible string and based on that, you draw a rough structure. Once you draw that rough structure, now take the individual strings and analyze the string properly. That what should happen if I add this transition here? Is there any other string that is being accepted? If it is accepted, then definitely you cannot add that string. See, one more thing that is to be taken care of, and that is the most important part, that is while you are drawing a DFA, for this particular statement, this could also be a particular DFA. See, if you feed any of those strings to this state, what will happen? It will be accepted by this string. But is it a valid DFA? No, I can never say that this is a valid DFA. Why? Because this DFA is accepting those strings that are within this language, but it is also accepting those strings also which are not in the language. Say for example BB. Is BB belonging to this language? No. But is BB accepted by this DFA? Absolutely yes. See, you have added a self loop. So you will always have to remember, whenever you are drawing a DFA, it should accept only those strings only that are within the language, and it should always reject those strings that are not within the language. So this is definitely not a valid DFA for this problem statement. Focusing on next, acceptance. See, acceptance can be of two types. First category is acceptance of a string by a finite automata. As in the previous example, we have taken this DFA. Suppose we want to check whether if we take a random string like ABAA, and we want to check whether this string is being accepted by this DFA or not. Let me just number those states, Q0, Q1. Both these two DFAs are same. Just to explain, I have written. So we will be scanning the string from left to right. The first symbol that we encountered is A. Where were we? We were initially at Q0 state, and the first symbol we encountered was A. So as per the DFA, Q0 on getting a A, it will move to which state? Q1. After that, the next symbol that was encountered was B. Then Q1 on getting a B, as you can see, it is moving to state Q2. Okay, I moved to state Q2. After that, we are now presently at Q2 state. Now Q2 on encountering the third symbol, we saw that Q2 on getting a A, it moved to state Q3. Finally, on encountering the fourth symbol, we found out that Q3 on A, it is remained in the state Q3 only. Is there any other symbol left? No, there is no other symbol that is left to be scanned. So I will be remained in this state Q3 only. Now you have to check whether this Q3 is a final state or not. If it is a final state, then definitely the string is accepted by the DFA, and if it is not a final state in case, then it will be rejected by that finite state. It will be rejected by the DFA. In this case, Q3 is my final state, so definitely I will be accepting that string. Now this is one way of properly representing. If we represent this thing only using a transition function, then what we can write? We can write it something like, this is the transition function symbol. After that, within the bracket, which string I am feeding to this machine, that is, in this case it is ABAA. I'll simply write it as ABAA. After that, what is the initial state? The initial state in this case is Q0. So this is how we make a representation. Next, this is the initial state, and this is the first symbol that is to be scanned. So we will be simply writing it as so it happens to be Q1 on getting a A. So the transition function remains the same. That is Q1 on A, where it is moving on to, it was Q0, sorry. So Q0 on A, it is moving on to Q1. So I'll simply write Q1, and we have already scanned the symbol A. That means now I will be omitting this part. That means the remaining string remains to be BAA. Next, Q1 on getting a B, where it should move on to Q1 on getting a B, it is moving on to Q2. So within this transition function, I'll write here Q2, and the symbols remained is, or the string remained is AA. After that, we will be taking up this symbol and this state. What we found out that Q2 on getting a A, it is moving on to Q3. So we will be simply writing it as Q3 and the symbol left only is A. Finally, Q3, that is the final state on getting a A, what we are left behind is only the state Q3. So whatever I had said before, that is only I have represented here in terms of a transition function. That is what is said in the line, that is acceptance of a string by a finite automata. On scanning the entire string, if we reach the final state from the initial state, then it indicates that the string is accepted by the finite automata. And as I have discussed before also, acceptance, when can I say a language is being accepted by the finite automata? I can say this line only when the automata or the DFA accepts all those strings that are within the language and rejects all those strings that are not in the language. As you can see in the example we had taken before, that means this one, this DFA accepted everything, every possible string that is over can be that can be possible with symbol A and B. It is accepting all such strings. But is the condition saying that? No. The condition says that it should accept those strings only which is containing ABA as substring, and it was accepting everything. Now you see, is it a valid DFA for this condition? Absolutely yes, because it is accepting all those strings that are within the language and at the same time it is rejecting all those strings that are not within the language. So this is what is being said in this acceptance of a language by a finite automata. That is, if all the strings in the language are accepted by the DFA and all the strings that are not in the language are rejected, then a language is said to be accepted by the DFA. Next is my non-deterministic finite automata. So till now we have, if we see the classification, till now we have discussed the DFA. That means under the category finite automata without output, we have declared DFA. We have discussed rather DFA. Now the NFA. See, the NFA is, the full form is non-deterministic finite automata. By now you know what is a finite automata, but what is this non-deterministic? Earlier it was deterministic. That means in non-deterministic, a particular state on getting an input symbol, this state on getting an input symbol, say for example if the input symbol in this case is A comma B. So this particular state on getting an input symbol, it might happen that it might move to no other state or it might move to more than one state. See, that is what it is written. Since it is coming under the classification of finite automata without output, so it will also be sharing that same definition, that it is expressed in a 5-tuple form. All the 4 things remains the same, that is Q, sigma, Q0, F, everything remains the same. The differentiating factor that comes into picture is the transition function. Earlier in the case of a DFA, what we saw is that a particular state Q on getting an input symbol, it used to move in one unique state only. But now in this case of NFA, it can move to more than one state. Now what is this 2 to the power of Q? This 2 to the power of Q is the power set of whom? Power set of this set Q. That means suppose if the set Q contains 3 states, that is Q0, Q1, Q2, then a particular state on getting an input symbol, it might move to, it may happen that it is not moving to any of the states. So in that case, this would be applicable. Or it might happen a particular state on getting an input symbol, it is moving to Q0, or it might move to one single state, that is Q1, or it might move to Q2, or it might move, in each of these cases it is moving to one state. But it might also happen that a particular state on getting an input symbol, it is moving on to more than one state. See, Q0 and Q1, or it might move to all the three states. That means Q0, Q1 and Q2. That is why we have shown this in a power set form. That means the main thing is that a particular state on getting an input symbol, it might move to no state, or it might move to more than one state. Let us just take an example. Can I call this as a valid NFA? Definitely yes. As I have said, a particular state on getting an input symbol, it might move to more than one state. That is what is happening. Q0 on getting a A, it is moving to Q0 also, and it is moving to Q1 also. This is where the non-determinism comes into picture. That means for a particular input symbol, there are more than one ways that needs to be evaluated as. Then if I take Q1 state, it might be possible that Q1 on getting an input symbol, it might move to one state, or in this case, as you can see that Q1 on getting an input symbol, it is moving to no other state. That means no other transition is only mentioned. So we can call it as a valid NFA. So there are few points that needs to be remembered when we are dealing with an NFA. Let's see. The first is that the NFA from a given state on a given input symbol, there may exist zero number of transitions or more than one transition, as I have discussed before. The second one says that NFA follows acceptance by final state mechanism. You just keep a hold on this point. When we take an example, I will be discussing this point later on. Next thing, in NFA, there is no case of a dead state. See, dead state, where this is needed, you need to understand. If you go back to DFA part, where does the dead state come from? Suppose if I give you a condition that construct a DFA over sigma A comma B, where it should accept strings that start with an A. That starts with an A. If this is the condition, that means the input symbol is A comma B, and the condition it should accept those strings that starts with an A. That means if I feed a string that starts with a B, it should definitely reject it. Then in that case, what the language should contain? Is there any zero length string possible? No. Is there any one length string possible? A. Then two length string AB or AA, and so on. I won't be writing much because I know that this is an infinite language. So for this, what the condition says that it should start with an A. That means as soon as it sees the first occurrence of A, it doesn't care what comes after that, it will no matter accept it. That means if A comes, I will simply move to the final state, and whatever comes after it, I will simply accept it. But what if from the initial state a B comes? Do I need to check what comes after B? No, because the first condition is not only fulfilled. The first condition what says that starts with a A. Is B starting with a A? No. What will happen? If it starts with a B, no matter what comes after it, I will simply move it to a state where no matter what simple input symbols come, I will remain to this state only. And this state, as you can see that this is an intermediate state, that means there is no option to come out of this state. Hence, it will be stuck in this state only. That means I can say this state as a dead state. Why am I calling this state as dead state? Because once I enter into this state, all the transitions thereafter are confined to this state only. If, as you can notice that from this state D, there is no possibility to come out and to move to any other state. That is why I am calling it as a dead state. So dead state case can happen in a DFA, but definitely not in case of a NFA. That is what is discussed. Next is, in NFA, given on an input symbol, multiple paths may exist. It is a repetition of this first point only. And next point says that in an NFA, for a given valid string, multiple paths may exist. If I take an example, say for example, I say that it starts with an A. Okay, if I for a consideration, we take that as ends with an A. We take a minor modification, ends with an A. It is just taken. We exclude this and we construct an NFA based on input symbol A, B, such that it accepts those strings that ends with an A. What will be the corresponding NFA for that? The corresponding NFA would somehow look like this. No matter the string starts with an A or a B, I don't care, but it must end with an A. So this is the basic criteria which is being fulfilled. I don't need to see for a particular state on an input symbol multiple transitions has been declared, because it is valid in case of an NFA. So this one suffices the condition. If I look properly, now if I feed suppose a string, that means I am feeding a string something like AE. Now what will happen? How will I check why this point is being set? That is what I am discussing now. Final state mechanism. Let us just see. Initially we are at state Q1, and at Q1, on getting the first symbol A, now we have two choices. First choice is either I can remain to state Q1, okay, I will remain at state Q1, or I can move to state Q2, Next, we will be evaluating both these two states for the second symbol and see to which state we are heading to. That means we will be taking into consideration the second A and evaluate for both these two states. That means on scanning the second A, Q1, on getting a second A, where it can move to, again it has got two choices. Either it can remain in the state Q1 or it can move to state Q2, and Q2, on getting a A, is there any other state or any other transition defined? No, we don't have anything defined. So it will be an empty state, since we do not know where to move on from a state Q2 on getting a A. So this remains the empty set. Now you see the final set of states that you have achieved. First is Q1, Q2 and an empty set, rather I should say. Now is this set containing a final state? Obviously yes, because this is a Q2 is a final state. So what will I say? That yes, this string is being accepted by the given NFA. If you had taken AB and evaluated something like in this way, you would have found out that the final set of states that you are achieving doesn't contain this state Q2, and that is why you will be saying that okay, that this string is not accepted by this NFA. That is why it is written over in the second point that NFA follows acceptance by final state mechanism. This is how we check for a acceptance. And this point, as it says that in NFA, for a given valid string, multiple paths may exist. See, once you have reached to Q1, there are multiple paths on getting an input symbol A. Either I can stay in Q1 state or I can move to Q2 state. That is why it is written that for a given valid string, multiple paths may exist, but at least one of them should lead to a final state. And the second last point is that the string processing time is high. Obviously it is high. Why? Because I have to evaluate each and every string or each and every pathway. That is why in that case the string processing time is high. And finally the last point says that minimization algorithm cannot be applied on an NFA. Minimization algorithm, if I, in a concise way, if I explain it, then minimization, where do I need? When we want to reduce the number of states in case of a DFA, there we make use of the minimization algorithm. Let us just see an example. See, construct an NFA which accepts strings that ends with an AB. So the preliminary rules that were discussed in case of a DFA remains the same. That is, you have to define the sigma and the language as it is. And next, what you have to remember is that you have to fulfill the basic criteria for this NFA. That means it must end with an AB. As soon as you read this line ends with AB, that means no matter what the string is starting with, it must end with an AB. That is what is happening. No matter what combination of A and B occurs, it must end with an AB. So the basic criteria should be fulfilled, rest everything will fall into place. Next question is, the construct an NFA which accepts strings such that last two symbols are different in a string. There also the first two procedures remains the same, and based on that you will be designing the NFA. And what the NFA says that the last two symbols are different. That means if I take the smallest possible string AB, AB is accepted by this NFA? Yes. Now you might be having a question that why can't I add this B transition in this, or why can't I add this input symbol B in this transition only? Even if you try to do it, what will happen? If I add this input symbol, then BB will also be accepted. That is why we cannot add this input symbol into this transition. We have to create a separate state, and we will be drawing the NFA as follows. One more question that you might come across is, why do we need one single final state? It might happen that I might create multiple final state. This final Q3 for accepting that strings that ends with an AB, and I might create another state named as Q4 that accepts strings that ends with a BA. Yes, that is possible. In that case, two final states will be declared. No problem, but we can reduce the number of states later on using that minimization algorithm. So this is how we define, based on a given condition, how to draw a NFA for a particular problem statement. Next is conversion of an NFA to DFA. So as far as this lecture is concerned, we have completed the DFA and the NFA part. Now what I need to do, if I want to convert a given NFA into a DFA, then we will be making use of this subset construction method. Now how does this subset construction method works? Let us just see. In a subset construction method, if you look carefully, it says that you start from the beginning state of an NFA. So, okay, let us just discuss the steps first, and then we will be taking up an example. So the first step says that start from the beginning state of an NFA. If I take this example, this is an NFA. How did I find out that this is an NFA? See, for this state Q0, it is moving on to more than one state for a particular input symbol 0. In this case, the sigma given is 0. The input symbol is 0, 1. So as you can see, for this state Q0, on getting a input symbol 0, it is moving on to more than one state, that is Q0 and Q1. Okay, now there are two possibilities. Now this is what? This is my transition table. See, there are two ways of representing a DFA. Whenever we are given a problem statement, based on that, using a directed graph, we will be drawing a DFA, or next we will be mentioning this transition table. Now what this transition table must contain? In the rows part, it must contain what are the present state. That means what states you have used for. In this case, there are 3 states, Q0, Q1, Q2, and on getting an input symbol, to which state it is heading on to. So as you can see, it is mentioned that Q0 on getting a 0, it is moving on to 2 states, that is Q0 and Q1. So this is what a transition table says. Transition table is nothing but it keeps an account of what are the states that you have made use of and to which state it is heading to on getting an input symbol. That is what is shown. So there are 2 ways of representing a NFA or this conversion concept. Either in the problem you will be given a table, transition table of an NFA, and then you will be asked to convert it into a DFA, or it might happen that you will be given in the form of vertices and edges form NFA, and you will be asked to convert it into a DFA. So it depends on the question itself. Let us just see. So what the algorithm says that start from the beginning state of an NFA, take the state within this third bracket. So what you do is that in simple terms, you just copy this first row as it is into the DFA. That means your DFA is going to contain 3 states. That is, first is Q0. If you are seeing that the present state on getting an input symbol is going to more than 1 state, in that case what you do is that you club these 2 states into one single state and enclose it within this third bracket. So what happens? It means that a separate state Q0, Q1 has been created. So the simple thing, you first copy the first row as it is. Next what you do is whatever states that are undefined now, that means whenever you are copying this first row here, obviously Q0, Q1 and Q2 are not defined. So what next you do, you start defining Q0, Q1 and Q2. So how will I find where to move on to if the state is Q0, Q1? There is no as such state Q0, Q1. So what you do is that for a particular input symbol Q0, Q1, you just club or make a union operation or perform a union operation between these 2 rows. For an input symbol 0, make sure you are making that operation perform on the rows Q0, Q1 only, not on some other rows or not for some other symbol. Whenever I want to find out to what state Q0, Q1 must head on to for an input symbol, you just do a union operation between these 2 rows for an input symbol 0. What I found out is that a new state has been created, Q0, Q1, Q2. See, that is what I have written here. And as soon as we perform the union between these 2, Q1, Q2 also got created. Now, till now, we have defined Q0, Q1 only. And up till now, what are undefined? These 3 states have been undefined. So keep on defining as it is. And at the end, if you find no other state that needs other definition, you just stop that process here, that itself. That is what is written in the algorithm. Place the next states for the beginning state for the given inputs in the next state column and put them in this bracket. If any new combination of state appears in the next state column, that means in this part, if any new state is being created, then you define it in the present state. That is what is explained. Okay, if in the present state column more than 1 state appears, then the next state for that combination will be the combination of the next states for each of those states. That means if a new state has been created which is a combination of these 2 states, Q0, Q1. Now separately I don't have Q0, Q1 state together. What we will be doing? We will simply perform a union operation for this input symbol 0, and the resultant would be the state it should head on to for the input symbol 0. That is what is said. You repeat those process up till when? Unless and until you find any other new state, you repeat that process. That is what is written over here. Okay. If no new combination of state appears, then stop the process. And with this now, you have converted this NFA to a resultant DFA. But remember one thing, you need to define what will be the initial state and what will be the final state in case of an NFA. What will be the initial state in case of an NFA? It will be same as that of the DFA. Sorry, the initial state in case of a DFA will be the same as that of an NFA. So no changes here. What I need to remember is that in an NFA, whichever is the final state, in case of a DFA, those states in which this final state will be associated to, those will become my final state. If I repeat it, what can I say? In this NFA, this star indicates the final state. That means in the corresponding DFA, whichever state contains Q2 as an element, those states will be considered as my final state. That means here Q2 is going to be my final state, here Q2 is going to be my final state, for this one also Q2 is going to be my final state. So in case of an NFA, there was one single final state, but in case of a DFA, we have 3 separate final states. So this is how we make a conversion. And finally, we will be taking up this minimization. See, once you have converted an NFA to a DFA, or in the very first chance you have designed a DFA, it might be possible that you have taken 6-7 states into consideration, although that same machine could have been designed using 4 states. Why would I take 7 states into consideration when I can perform that same thing with the 3 states? So there I need to make a minimization. So for that, we need to have some idea of some terminologies. First is that inaccessible state. Inaccessible state is what? A state that is not reachable from this initial state. Suppose we have a DFA, something like this. I have not named the states and the input symbol is A. Suppose it is only A. By any chance, can this state be reachable from this initial state? No. I can, from this initial state, I can reach to the second state, but in no way we can reach to the final state. Or rather, I should say this state, this third one state. So what would I say? That this state is an what? It is an inaccessible state. Next is what? Equivalent states. Now, when can we call 2 states as equivalent state? These are what? These are my 2 states. I am making a comparison. Whenever we are using these terminologies, that means we are making a comparison between 2 states. So 2 states which are named as Qi and Qj are equivalent if on scanning a string X, this X is what? This X is my string. So 2 states Qi and Qj on scanning a string X, if both of them reach to final state or both of them reach to non-final state, then only I can say what? Then those 2 states Qi and Qj are said to be as equivalent state. Now what is this? X belongs to sigma star. This is what? This is the closure of, rather it is the cleans closure of the input symbol. Whatever input symbol that you have used, either it may be sigma equals to AB. So any of the string that is possible with this 2 elements A comma B, if on scanning those strings Qi and Qj, both of them either reach to the final state or both of them reach the non-final state, then I can say that those 2 states are said to be equivalent state. Next is distinguishable state. Distinguishable state, when can I say that those 2 states are distinguishable? If one of them reaches to the final state and other reaches to the non-final state, or the vice versa. If something like that happens, then I can say say that, okay, I can call that Qi and Qj states are what? These are called as distinguishable state. Now, then what is this K equivalent state? This K equivalent state and this equivalent state, both are, you can say, they are related to each other. How come? K equivalent state states that if two states Qi and Qj on scanning a K-length string, either both reaches to the final states or both produces a non-final state. That means this K is what? K indicates my K-length string. That means on scanning a K-length string, if both of them reach to the final state or both of them reach the non-final state, then I can call them as K equivalent states. So one thing that is to be taken care of, that whenever I am calling it as both produce final state or both produce non-final state, it is not mandatory that both Qi and Qj both are reaching to those same final state. It might happen for a given DFA there are more than one final state. It might happen that a DFA contains 4 final states. So Qi and Qj might reach or might end up to 2 different final states. That is okay with this condition. Then also we can say that these 2 states are equivalent states. So let us just take an example of minimization, or let us just first take the example with me. Okay, suppose this is a given DFA. If you look carefully, all these 4 states have been, rather all these 5 states have been defined, where to go for a A and where to go for a B. But I don't know whether this problem could be solved using less number of states. Let us just take the example of minimization. Minimization says that the first rule or the first step is that exclude all those states that are inaccessible from the initial state. Is there any state that is inaccessible? No. I found out that all the states are accessible. Okay. So the first condition is fulfilled. Next is that divide the set of states into 2 subsets, that is final state and non-final state. So what I'll do, in the very zero equivalence state, I will be making a partition. That means there will be 2 states, 2 category of sets. First will be the set of final state. That means for this case we have only one final state, that is Q4. So in one set I have kept Q4, and in other set we have kept all the non-final states, that is Q0, Q1, Q2, Q3. So we have kept it in one other set. Next, what we will be doing is the next step says that apply all the inputs separately on 2 subsets and find the next state combination. If it happens that for applying input on one set of states, the next state belong to 2 different subsets, then separate those. If you didn't understand this English, no problem, we will take it up. Now in the next one equivalent state, what you do is that you take single in a way, you compare these 2. First you compare Q0 and Q1. You see for A and for B, is there any case where they are moving to 2 different set? See, Q0 and Q1 on getting a A, see it is moving to Q1, which is in same set only. And Q0 and Q1 on getting a B, they are moving into Q2 and Q3. Q2 and Q3 both are into one single set only. So they don't need to be partitioned. They can stay together. No problem. Next, Q2. Take Q2 into consideration and see if this state is eligible to stay with Q0 or Q1. You can take randomly any of the states. Let us just take Q with Q1. Let us just make a comparison with Q1, Q2 and Q1. See, if you check, both of these are remaining in the same set. So Q2 and Q1, or I can say Q2 can reside in the same set, no problem. Next, what you do, see if Q3 can reside with Q2 or not. Let us just check. If you check, then you can see that Q3 and Q2, okay, For A it is not a problem, but for a B transition, see, Q2 is going to Q2 and Q3 is going to Q4. That means both are belonging to two different sets. That means Q3 is not eligible to remain in this set. That means what we will be doing, we will create it Q3 as a separate set. Is this the final set? No. I will be comparing up till a point where there is no question of minimization. Let us just check for a 2 equivalent state. Next, what we will be doing, we will be repeating that same step, but this time we will be taking this into consideration. While we were trying to find out the 1 equivalent state, we used to refer to this 0 equivalent state. But while we are finding the 2 equivalent state, we will make use of this 1 equivalent state. And what we will be doing, we will be checking that for a particular input, for input symbol A, are both going to that same set. If yes, then both can reside together. If no, then both can't reside. Then you have to create a separate state. For how much time I'll do? I'll do it for, or I'll repeat this step until and unless I get a point where there is no question of minimization. So after 3 equivalent states, if you repeat 4th, 5th, 6th, then also you will find out that Q0 and Q2 will remain together only. See, this was a problem that you had solved using 5 states, but after minimization, what I found out that it will be solved using 4 states only. So when you can solve a problem using less number of states, then why to use larger number of states? We can solve it using less number of states. So this is what I had to discuss on finite automata. With this, I'll conclude the lecture. Thank you.